The next topic is Gaussian mixture models. They are really interesting, and the interesting part is that for the same task, if we want to detect these fraudulent transactions, we can use a model that doesn't even want the labels. It says, I can find these fraudulent transactions even if you don't tell me that they are fraudulent. And the model is therefore unsupervised learning. So, but the idea is very simple. The idea is that we fit a Gaussian distribution, which is just a normal distribution, to this data. And as there are more data points here, that distribution will fit somewhere around here, and then the likelihoods associated to these data points will be tiny. So let me tell you about the normal distribution a bit. So this is normal distribution for univariate data. So X is only one feature, and the y-axis represents the density of the distribution. So as you can see, it looks like a bill, but it is in 2D because our data is only one-dimensional. X is only one-dimensional. But we have multivariate Gaussian, which exactly looks like a bill. So this is multivariate Gaussian. It is in 3D because our features is two-dimensional. Here we have some x1, which is from -3 to 3. We have some x2, which is also from -3 to 3. And the height of this bill represents, again, the density of this function. Right? So you can see that, for example, in the middle of the distribution, in the center, the density is like 0.15. For a data point, closer to this kind of further in the periphery of the distribution, the density or the height of this bill is a small value, it's like 2%. And then for the data points that are outside of here, which means that they are further away from the center of the distribution, the likelihood is even less than 1%. So that's what we can use. We can just fit a distribution, fit a Gaussian distribution to this data. It's going to fit to this core of the data, so we call this core, and these outliers are in the periphery. So it's going to become some 3D bill that just, fits to this data, right? So just imagine some 3D bill that is here, centered here, and then as we go to the sides, the likelihoods become smaller and smaller because the bill, the height decreases. So then we just use the likelihoods that we have for each point as some sort of a score. Whenever the likelihood is less than 1%, we call it fraudulent. That's it. That's using some unsupervised learning method for anomaly detection or outlier detection.
Are also similar. So in that case, they will also have a high density distribution, right? Like both. So
I got it. Yeah. So sometimes we're dealing with data like multimodal data like this. So the two classes are both, kind of common observations. Then we don't call this anomaly detection. But still, we can use a Gaussian mixture model, but with two components, meaning that we want to fit two bell curves. One of them fits here, and one of them fits here. Let me just draw it again. So let's say that we're dealing with some distribution. The histogram for that distribution looks like this. There is some mode here, and there's, another mode here. This is bimodal, some bimodal distribution. If we fit two bell curves here, one of them fits here, and one of them fits here. Then we can, first of all, we can separate these. And second of all, if there are some outliers, we can also see that those outliers have tiny likelihood for this and tiny likelihood for this. So they are outliers. Yeah. In the case of this credit card fraud detection, it's actually simpler because most of the credit card transactions are valid, and the valid transactions have a range of dollar amount that is reasonable, maybe a 2-digit number to like a 4-digit number. But suddenly, if there's like a credit card is charged is charged $100,000, of course the transaction will be blocked by some system because it's suspicious. Or if the card is charged at like 3 a.m. for the time zone of the credit card holder, it will be blocked. If you have traveled to a different time zone, maybe the first time you tried, getting an Uber from the airport, maybe it didn't work. That's possibly one reason. Yeah. All right, so for anomaly detection, we have essentially binary classification because either an observation is kind of normal or an anomaly or an outlier. So in that sense, it's binary, but there are also situations where this is one class, this is a different class, and outliers are a third class. Yeah. So, right, yeah. Yeah, definitely. They can also overlap, and that's fine. Then, then if you want to make a classification, we classify based on the curve that is above the other one, right? Because it has higher likelihood. So, if they overlap, and you want to make a prediction for this. This is, let's say, class 1. This is class 2. You check that the likelihood for class 2 is this. The likelihood for class 1 is this. So you classify to class 1. And actually, finding this sort of point is really important. In many situations, you're dealing with some range of values, and you want to just classify them to two classes without really selecting an arbitrary threshold. Let's say you have reviews. You have two different you have reviews of episodes of a TV series, and we just kind of naturally we think of a good episode and a bad episode. But where to put the threshold? Is it 7? Is it on like IMDb score? Is it 7, 6? We have an example on that. Right. So, yeah. For this one, a new category. Yeah, I mean, depending on the context, it may make sense to do something like that. If you want to have something in between, let's say good and bad, you say a moderate. Yeah, you can do these things depending on the situation, but the thing is, also these models work without doing those things, because in some situations you have these classes are predefined. So this is the kind of distribution of length of tuna fish, and this is the distribution of length of salmon. So we can have fish of different sizes, you know, for each type, and clearly there's an overlap. But eventually, when you want to, you know, put a price tag or something on it, you want it to be either tuna or salmon, and just the fact that there's a range of, you know, size, length of fish that kind of is expected for both of them doesn't mean that the fish is both a salmon and a tuna. Yeah. Right. So let's go over the code. Let's go over the code. So here, first I'm going to just create some synthetic data. I'm going to create 400 data points and call them the core. And I'm going to create 10 data points as outliers. So here everything is simulated. So even without a machine learning model, you can see that this is the core, and everything else, like these are outliers. I generated them, so I know, right? But in the application, we have some data. It is high dimensional, so we cannot plot it. That's why we need the machine to be able to separate the outliers from the rest of the data. Here, exactly 400 of them are generated with a small standard deviation. That's why they are all populated here. And 10 of them are generated with a large standard deviation. That's why one of them is here, one of them is here, one here, one here. And if you check these, they are exactly 10. So a machine learning system that can distinguish these from the rest would be an anomaly detection system. So when we look at X, so for the data, so this is bivariate data. So we have two features, right? So both the horizontal axis and the vertical axis were features. So these are some of the data points that are in the core. You can see that, for example, on the horizontal axis, it was 4. On the vertical axis, it was 1. So 4 and 1. So 4 and 1, right? So it was one of these x's in here. And the outliers, I added them at the end of the data. So if we check the end of this, you can see that there are some data points like at the end of the data, where is it? So at the very end, we have these data points like 6.3, and this is 10 to the minus 1. So 6.3 and 0.4. So this is something that is separate from that core. It's somewhere else, right? Again, it's obvious for us to see, but we want to automate this process so that even if there are more than 2 features, we can find them as anomaly. So what we need is to find the mean and the variance of these 2 features, right? We can calculate them using this function. This gives us the mean, and this gives us the variance. You can also use the functions that are available in Python. So, and then this is the part that is not that exciting, but the formula for this nice shape doesn't look so nice, just like anything in mathematics. The graphical representation is just gorgeous, and the formula is ugly and grotesque. So this is the formula. This is the mathematical representation of the same curve. So this is also called the probability distribution function or density function. So we need to just calculate this for every single data point, and that would be the score, that would be the height, that would be the likelihood. So here I have it, and of course also in the code it doesn't look nice, but that's just the formula. Now that I have this function, which was a function of the variance and the mean, now I can calculate it for every single data point out of those 410 data points, and you can see that, for example, for the very first data point, it's 0.11. 0.11 is somewhere here. So that first data point was something that is, around here. In terms of likelihood, it has a relatively high likelihood to belong to the core. For the outliers, which were at the very end of my data, their likelihoods are really tiny numbers. Like this one is 1.2 times 10 to the power of minus 34. So it's 0.00000, almost 34 zeros. So that point is something that is, so, further away from here that its height in 3D is a really tiny number so close to zero. So that's an outlier. So now that we have these kind of scores, these likelihoods, we can plot them. We can just color the points based on those likelihoods, and you can see that the core, data in the core takes, some light colors, and these outliers in the periphery, they get some dark colors. So if we use a threshold, something like 1%, then we can separate these. So I used a threshold of 1%, rather arbitrary for now. And you can see that here I've kind of marked those whose p value is smaller than epsilon. I've marked them with a red circle, and you can see that exactly those 10 outliers are marked in red, which means that my classifier, which is unsupervised learning, has a precision of 100% and recall of 100%, and F1 score of 100%. So you might be wondering, well, this is unsupervised learning. How can we measure these? How can we check whether something is correct or not? While this is unsupervised learning, after making a prediction that this is outlier, we can bring the label to check whether the prediction was correct or not. So it is unsupervised in the sense that the model says, I don't even want to see the labels. I'm so smart, I will figure it out myself. But then for making the predictions, for evaluating the performance, we check the predictions against the classes. So we can have like an indicator of whether something was indeed an outlier or not. All right, so, yeah. It was a very arbitrary choice, but let's just try other values. If I try 5%, I'm selecting all the data points who have likelihood less than 5% as outlier. So what do you think happens? Will I get more outliers or fewer outliers? More, because I'm making the model more sensitive. So here is the more sensitive model. Oh, sorry. Yeah, you can see that it also now flags some of these as outliers. So between these two choices, 1% is a better choice because we know the ground truth, so we can compare to it. If I try a value smaller than 1%, maybe something like this, there's some chance that we miss some of the outliers, right? Now we missed this and this. So our precision is still 1. Now our recall is 80% because we detected 8 out of 10 outliers. So this model would have the best performance if the threshold we use is suitable. So another idea is not just coming up with some arbitrary number, but instead of an arbitrary number, we just sort the likelihood values we had. We just sort them and pick one of the smallest values we have, right? If we know, for example, that out of 410 data points, there are 10 outliers, what we should normally do would be dividing, 10 to 410, whatever value this is. So this is something like, I guess, 2% almost. Then we should just rank those, just sort those p-values and pick the value at the second percentile of that distribution. The median is at the middle of a distribution, is 50th percentile. Second percentile, it means that when you chop a distribution in 100 pieces, the index at place 2. That's where only 2% of the distribution is smaller than it. So we can use this idea. For example, here it asks, what happens if we just sort these p-values and pick the fourth smallest value as the threshold? Well, then we're going to detect 4 of the outliers and miss 6 of the outliers. Our precision will be 100%. Our recall will be 40%. Recall is 1 minus how much we miss. We missed 6 out of 10. All right, so, and then it also asks what is the highest value of k where we can still get a precision of 100%. So just to answer these 2 questions, I have this piece of code. Here, if we use 4 as the threshold, so I'm sorting them, right? So the sorted P looks something like this. The smallest value we have is at the beginning of this. You may remember we had something times 10 to the minus 34. It is sorted. So when we say we pick the 4th smallest value, it means we pick this as the threshold, right? Therefore, we're going to pick this, and this as outliers, and then everything else as normal. So, yeah, any questions so far? Yeah. So the general application is detecting any sort of anomaly, any sort of strange sort of patterns in the data, which is actually very common. So one of them is like detecting fraud, but for finding outliers in the data, this is like the go-to method. Another situation is where your data where your data set is unbalanced, and then the case that you're looking for is just so uncommon. For example, credit card fraud. Well, 99, I guess, % of credit card transactions are valid, right? So a method like this is suitable because what we care about, which is fraud, is so difficult to find in the data. So we want a method which is sensitive to detecting, unusual patterns. So actually, there are many applications to it. I can just think of these for now, but if you post your question on Piazza, I can also look it up and hopefully find more relevant applications. Yeah. Yeah. Yeah, so that's right. Actually, in your project, you have something that looks a bit similar to this. So you want to see whether some missing values in some variable, whether they are missing by chance or missing at random. That's really important because when you start working on a project, you see that in the data set, someone just had put underscore instead of a value for some of the data points. So it's a mystery, and how you deal with that mystery has huge effect on the final model. Yeah, so you definitely see it. All right, so now I'm going to move on to something a bit more complicated. This is where we have 5 cores of data, and we want to detect the outliers. So let's say our data looks like this. So the code was such that it creates 5 sort of new clusters of data, and then outliers based on the same centers but with higher variance, right? So now here, again, I'm playing God. So I have 400 data points which are normal, and there are 50 data points which are outliers. So again, if the scatter plot is 2D, we don't even need machine learning. We just look at it and say, oh, this one looks off. This is outlier, right? So this is just for demonstration purposes so that we can kind of visually confirm that, oh, yeah, the machine is doing something that is also intuitive to me. Otherwise, in the real application, this can be a 10-dimensional Gaussian distribution. So we had 1-dimensional and we had 2-dimensional, which looks 3D. But this Gaussian distribution can also be in 10 dimensions. It works because in 1 dimension, you have variance, which is a number. For example, the variance of this distribution is 1. And for this distribution, instead of one number, you have a matrix. So moving from 1 dimension to 2 dimension is moving from number to a matrix. Now, if you can imagine a matrix that is 3 by 3, this thing means a bell that is in 4 dimensions. And a larger matrix with just 10 rows and 10 columns means that a Gaussian distribution in 10 dimensions. It definitely exists mathematically. We just cannot wrap our heads around it. And that's where actually the application is, So again, here, as we know that we created the data with 5 clusters, it's kind of obvious that we should fit 5 of these curves to it, right? So, but first, naively, I'm going to just fit 1 Gaussian distribution and see how it works. With 1 Gaussian distribution, it's going to fit to all of these, kind of takes all of this as the core, and only detects these outliers that are so far off, and the outliers in between the cores are not detected. This is kind of expected, and this was performance on the training set. We also had like a validation set. On the validation set, again, the performance will be poor. This is validation set. And again, the outliers in between are not detected. But we just need to use 5 components because we had 5 cores. So we use a Gaussian mixture model. So the mixture means mixing multiple of these bell curves. So we use 5 of them. Number of components is 5. It fits to the data. And now these are the cores that are detected properly, and anything other than the cores are detected as outliers. So this is now really good performance on the training set, and on the validation set, you can see that again it does a relatively good job. So you might be wondering, what is the performance of this method irrespective of the threshold. So we talked about ROC curve last time. Let's plot the ROC curve of that one component Gaussian, which was terrible, and that 5 component Gaussian. So here we have the ROC curves. For the one component Gaussian, this is the ROC curve in blue. And for the 5 component Gaussian, it's this orange thing. And you can see that the orange one is closer to the top left, which means it's a better classifier. It's a better classifier regardless of the threshold, right? If we want to further summarize this, we can use AUC, which is area under the curve. So AUC for this orange one will be very close to 1. So this is the AUC. This is using, this is one method of calculating it. AUC for the 5 component thing is 0.98, which means it's very good. For the other one is 76. And when AUC is a half, it means it's just a coin toss, right? So less than half is just embarrassing. So this is the same thing, just computed differently. So this was Gaussian mixture model.